Hi students, I welcome you all for today's discussion. Let us understand about thermal efficiency of Rankine cycle. For any cycle, we know the general formula of thermal efficiency. Thermal efficiency is net work by heat supplied. Let us apply this formula for the Rankine cycle. So in the Rankine cycle, as we have discussed in my previous lecture, steam turbine produces Wt amount of work. Part of this work is supplied as Wp to the pump. The net work interaction across the control volume of this Rankine cycle is Wt minus Wp. It is developed and it is consumed. Developed is always positive, consumed is negative. So net work developed is Wt minus Wp, and we are also supplying Q1 amount of heat energy into the boiler. So if you substitute this formula into thermal efficiency formula, net work upon heat supplied will be written as Wt minus Wp upon heat supplied is Q1. From our previous discussion, we know the formulae for all these parameters. Let's have a quick review on those formulae. Wt was discussed as H1 minus H2, and Wp, that is pump work, was discussed as HF4 minus HF3, and heat supply in the boiler from the furnace Q1 was discussed as H1 minus HF4. Substituting all these three parameters in the thermal efficiency formula. So for Wt, I wrote it as H1 minus H2 minus Wp HF4 minus HF3 divided by Q1 is written as H1 minus HF4. So this is the thermal efficiency formula for Rankine cycle. Thermal efficiency for Rankine cycle. Now let us discuss in detail about this term, that is pump work. From basic thermodynamics, we know for any isentropic process, the TDS relation is given by TDS is equal to dH minus VdP. Since pump work is isentropic work in Rankine cycle, so yesterday we have discussed in the TS diagram, 3 to 4 was the pumping work, it is isentropic. So entropy remains constant. Therefore change in entropy for this process is 0. Hence ds is equal to 0 in this expression. After substitution, we will get the equation as dH minus VdP is equal to 0. That is dH is equal to VdP. The same expression can be written as delta H is equal to V times delta P. Delta H is change in enthalpy across the pump. Change in enthalpy across the pump was here output enthalpy HF4 minus inlet enthalpy HF3. HF4 minus HF3. So we substitute the same expression for HF4 minus HF3. So is equal to the specific volume at the inlet of the pump is, state 3. The specific volume at the inlet of the pump 3 will be V3. So therefore this is V3 times change in pressure across the pump. So pumping process is 3 to 4 process. From HS diagram it will be very clear for us to understand. So 3 to 4 is pumping process. Okay. So here this pressure line is, constant pressure line is condenser pressure, and final pressure is boiler pressure. So this is P1 and P2. The change in pressure across the pump is P1 minus P2. So we are substituting the same formula for change in pressure across the pump, P1 minus P2. So where P1 is boiler pressure, P2 is condenser pressure. Students, if pressure value is in bar and specific volume is in meter cube per kg, then the above equation can be written as HF4 minus HF3 is equal to V3 into P1 minus P2 into 10 to the power of 5 joules per kg, because 1 bar is equal to 10 to the power of 5 Pascal. That is the conversion. The pump work HF4 minus HF3 is negligible when we compare the value of turbine work, that is H1 minus H2. Hence, sometimes we ignore this term and we modify Rankine cycle efficiency equation as H1 minus H2 divided by H1 minus HF4. Now, students, let's discuss about few parameters related to Rankine cycle. There is a first parameter called as work ratio. It is defined as ratio of net work output of the steam power plant to the positive work output. Therefore, mathematically we write it as work ratio equal to W net upon WT. The net work from the Rankine cycle we have already discussed. It is turbine work minus pump work divided by positive work is turbine work. This is about the work ratio. Another parameter, important parameter for steam power plant is steam rate. This parameter indicates the capacity of steam power plant. Capacity of steam power plant. Then how we define this parameter? It is defined as the rate of steam flow in kg per hour required to generate unit output shaft power, that is 1 kilowatt of power. So steam rate can be mathematically written as 1 divided by turbine work minus pump work. So many kilojoule per kg in the denominator. So if I write kilojoule per kg in the denominator, kg will move to numerator. So kilojoule remains in the denominator. If I divide and multiply by kilowatt unit to this unit, so the numerator kilowatt unit can be written as 1 kilojoule per second, because 1 kilowatt equal to 1 kilojoule per second. So kilojoule get cancelled. The remaining unit is kg divided by kilowatt second. So that is kg per kilowatt second. So this formula indicates so many kg of steam supplied to the Rankine cycle per second to generate 1 kilowatt of power. But what our definition says, kg per hour. Then how to convert this formula to kg per hour? The simple job is you have to replace second by hour. So we know 1 second is equal to 1 divided by 3600 second hour. So if I substitute 1 divided by 3600 in place of second here as a hour, so 3600 will go to numerator. So the final formula for steam rate is 3600 by turbine work minus pump work, and final unit will be kg per kilowatt hour. Now let's discuss about comparison between Rankine cycle and Carnot cycle. The first difference is on specific work output of the cycle. In Rankine cycle, we are able to produce higher specific work output than the Carnot cycle because the work supplied to compress the wet steam, see point 3 is in wet steam region, till fourth state is higher than the work supplied to pump the condensate from state to state 4 in Rankine cycle. So it is very less compared to that in Carnot cycle. So hence specific work output is WT minus WP. So if WP is more in Carnot cycle, final output will be less. So that is all about the first difference. Second difference, efficiency is lower than Carnot cycle. Rankine cycle efficiency is lower than Carnot cycle because Carnot cycle is an ideal cycle. So it has got higher efficiency than the Rankine cycle. Now pumping work is less compared to compression in Carnot cycle. So we have already discussed about this point. So 3 to 4 is lesser compared to Carnot cycle. So compression of vapor consumes larger work. That is about the third difference. So fourth difference is any type of steam can be used in Rankine cycle. So yesterday we had discussed any type of steam. So that is, this is the TS diagram. So 1 double dash superheated steam, 1 that is saturated steam, 1 double dash steam. So 3 possible conditions at the inlet of the turbine. Any type of steam can be used in Rankine cycle, but whereas in Carnot cycle only wet steam at the turbine inlet, that is first one, can be used. So fifth one, complete condensation of steam in process 2 to 3, that is in condenser. Completely it is liquefied, condensed till saturated liquid line here. So here little partial condensation, okay, so partial condensation, so 2 to 3, so state 3 is not on saturated liquid line, there is a partial condensation in the condenser. So this is all about the difference between Rankine cycle and Carnot cycle. Thank you.